Hey everyone, I'm Adam Kelly. In the last video, I showed you how to make this cool little single coin collector with Unity ML agents. You can see it's not perfect, but it has learned using neural networks to find a coin on top of a platform and then navigate to it, jump on top of the platform, and collect the coin. So this video, I'm going to show you how to convert this into a visual agent. So right now it's using raycasts, and let me minimize this so I can show you what that looks like. I have to switch into scene view. You can see these little white rays that are shooting out, and then when it sees the platform, they turn red. So it is basically shooting out these rays, and when they hit something, it gets that information back, and it's using that information to make decisions. And just as a reminder, we're currently observing elements in the scene, or elements, I'm just saying element because it shows it right here. We're viewing objects in the scene that are tagged with platform or collectible. And so that's how it's sort of seeing things in this scene. To change and turn this into a visual agent is actually very simple, which is great news. All we have to do is replace this ray perception sensor with a camera sensor. Now, I will note that by doing this, you're going to dramatically increase the size of your neural network because we're going to have a lot more inputs. We're going to have tons of pixels that are coming in instead of just these rays and the information that comes from those. So that's just something to be wary of. In my experiments, the neural network size was about 10 times larger. So it does take longer to train. And another warning is that if you're going to go down this path, having tons of cameras running at the same time in one scene can be pretty expensive. So if you're thinking about having an army of agents that are all using cameras, then take performance considerations into consideration so that you don't accidentally go down a path that's not going to work for you. If you're thinking about just having lots of agents in a scene that are performing the way you want them to perform, the simpler the observations, the better end result. And if you're putting this into a game, your users won't know the difference of whether it's using a camera or not, with the exception of if the game frame rate has tanked to a point where it's so low that it's basically unplayable. So we're going to start off with the state of the scene that it was in from the previous tutorial. So if you haven't followed up to this point, go ahead and check out the link to that. We'll make sure to put it in the description, and we will start from here. So we have this coin challenge area prefab. I'm just going to open this up, and I'm going to go to the character. The character is what has our behavior parameters, simple character controller, simple collector agent, all this, and most importantly, the ray perception sensor. I'm going to just completely remove this, and I'm going to replace it with a camera sensor. So if you type in sensor, it'll give you these suggestions, and we're going to do a camera sensor. So it wants a camera, makes sense. It wants a name, the default is fine. And it wants a resolution. So the resolution by default, they choose 84 by 84 pixels. You can choose to either go lower than this or higher than this, but be aware that the higher the resolution, the more data needs to be flowing through this neural network, and it's just going to get bigger and bigger and bigger, and you probably don't want that. So you want this to be probably as low as you can go while still solving the task. There's also grayscale. So by default, it's going to use red, green, and blue channels, but you might not need that much information. You may only need a grayscale version of that image for your neural network to work. So if that's the case, then you can turn on grayscale and it will be a simpler neural network. You also have observation stacks. And I don't know all of the applications of this, I'll admit, but one potential application is that if you have something that's moving in the scene and you want it to sort of see that movement, then an observation stack means it's going to show like 5 frames in a row if you set this to 5. I don't know what their suggested max is. Okay, 50. So let's say you wanted it to remember the last 5 frames at any, or not remember's the wrong word. If you want it to see the last 5 frames in a row, you would set this to 5, and then it could see the progression of this. Let's say this platform was actually sliding side to side. you could see which direction it was sliding by just observing the previous 5 frames. And as for compression, I've never changed this. PNG seems to work just fine. So I'm going to set up a camera now that can go into this slot right here. So I'm going to create a camera as a child of the character so that it moves around with the character. And we could just set it up to be like right here at like eye level. But one of the problems with this is it can't see right in front of it. And that may not be an issue in some cases, but in our case, if this were right up next to the platform itself, anything that's in here is kind of in its blind spot. And that's not my preference. And I think that the best solution in this case is to just move it back a little bit. So I'm going to position it along, oops, that's not what I intended. I'm going to position it in the Z direction so that it's behind the agent, sort of a third person view. I'm going to lift it up a little bit and I'm going to change the rotation in the X so that it can fully see the agent from behind. I know this camera preview is pretty small, so let me show you from here. So that's what it looks like. And you can just mess with it until it looks pretty good for your agent. Now, there's a lot you can do with cameras. You could make it so that your player was invisible to the camera if you wanted. There's tons of post-processing and stuff that you could do if you wanted to give it additional information. That's up to you. But the only change I'm going to make on the camera is to just increase the field of view to about 90. This is generally larger than you'd probably have in your game because it's different than the defaults, but I think this gives it a nice large field of view to work with. Now, if we go to here, we can drag this camera into here, and now it's set up. But we want to think about this resolution here, the 84 by 84. So if you go to this free aspect thing in the game tab, you can set up different resolutions. So I've already set this up, but you can click plus and you can feed in your fixed resolution here. And then once you hit OK, it'll show up in this list. And if I click on it, now we can see what that resolution looks like to the neural network. This is what it sees and how it's going to learn. This is lower resolution than you or I would ever want to play the game, of course. But the question is it good enough to play the game? So I think the easiest way to try that is just to change the behavior type in the behavior parameters to heuristic only. We'll hop back out to the scene and we'll hit play. And since we set this up so that we can use keyboard input, I'm going to use my keyboard and try and play this game. See if I can successfully collect the coin. And the good news is I can. It's really quite easy for me, even though the resolution is so low. All right, now how do we check to see what the lowest resolution is that would work? Well, we can try different resolutions. And I believe the lowest it can go is 32 by 32. So I set up one for 32 by 32, and let's see if I can play with that. It's not a great experience for me as a player, but I don't think it's necessarily going to prohibit me from successfully playing this game. And if I can play it, I think the neural network's going to be able to. Looking at that, it's pretty clear where the coin is, where the platform is. Obviously, we have that additional context, but the neural network just needs to learn that, hey, find a red-looking blob and find a yellow thing on top of it, and then jump when you get to a certain point. So when the red blob looks like that, then jump and move forward. It should work at 32 by 32. So let's give it a try. I've always done 84 by 84, but I'm going to try this for the first time here and just set the width to 32 by, whoops, not grayscale, 32. I'm actually planning on keeping it in color because I want in the future this to be able to work with different colors, like give some different context based on the color. Maybe a green platform means something different than a red one, or maybe you know, a gold coin looks a lot like a blue coin or something like that. I don't know exactly what I'm going to do with it, but I want to keep the color on. So now that we have this set up, we should be able to retrain it. I'll mention right now that since this was set up previously with the other neural network, if we just hit play, it's not going to work because it was trained to work with the ray perception. So like if I hit play right now, we should get a bunch of errors in the console. So let's see what happens. First of all, it's not moving. Okay, I'm just going to stop it and go to the console and see what the errors are. So first thing, it's complaining that there are 9 audio listeners in the scene. Well, that's worth fixing. So we will go in here and just go to the camera and we'll remove the audio listener. Remove that component. All right, and then I'm not sure, I was expecting some different errors to pop up, but I'm not sure why. It is saying that the vector observation size of the model does not match. Was expecting 52, but received 0 by 1. So I think what I was expecting to happen was we would get some error messages because this is the wrong neural network to be feeding into this, but we know that it's wrong. So let's just retrain this and get the right neural network and see what we can get working. So the training command for this is the same as from the previous tutorial. So we need ML agents learn, and you need to make sure you're in your ML agents directory in order for this to work, of course, but follow previous tutorials for that. We need to pass in the config file, config slash, what do we got? PPO, and then I want simple collector.yaml. Then -- run -id. And let me see, what was the last one that I did a test run of this? Simple viz 02. So I'm going to call this simple viz 03. Now this YAML file, let's take a quick look at that. This is the same as I was using before, completely unchanged. It's just the simple collector and a bunch of settings for the neural network. I want to point out this viz encode type. That's been here all along, but we haven't used it. This is saying we're going to use a simple visual encoder, which is basically a simple convolutional neural network that feeds information from the camera into our neural network. So if you go here, and I found a little bug in their documentation, if you do viz encode type, and you search for that, and you're trying to find the documentation about it, you'll find that all of their examples use viz encode type, but their markdown is missing anything in the documentation. And that's because they have a typo in there. They called it viz encoder type here in the training configuration file markdown. And I just actually submitted a bug for this. But basically, the simple default viz encode type uses a simple encoder which consists of 2 convolutional layers. And then they've got a couple other here, the nature CNN using CNN implementation. I'm not going to read all this. You can read it at your own leisure. And if you need to do more complex neural networks, this is the way to go. For now, this is a very simple convolutional neural network. It's not doing anything too advanced. So let's give this a try. Whoops, I opened the wrong one. We'll hit enter. On this command, it's going to ask us to press the play button in the Unity editor. So let's press play. And something's not right. Let's see, what did I forget? Nothing in the console. Oh, okay. I'm glad I made this mistake. So I like to leave these mistakes in because hopefully it's a good opportunity for you to learn if something like this happens. So if we go into our prefab again, we look at the character. I had changed this to heuristic only so I could test it. I need to change this back to default for it to work. And that explains why it wasn't working before, or why it wasn't giving an error message before when I had the wrong neural network in there. Just to show you what that wrong neural network looks like, let me show you. It should give an error message right now. Yeah, we're getting an error message. You can see down at the bottom, it's doing it over and over and over again. Usually go up to the top, look at the top one. So it says there's basically a vector observation error, which makes sense. It's trying to observe through the neural network that we trained on the ray perception with camera input now, which doesn't make any sense. It's not going to fit. So we need to retrain this. So I'm going to try this again. I'm going to increment my number here so that it will be happy. And we'll run this again. And we'll hit play. And hopefully they'll start bouncing around. All right, this is a good sign. So this is what the agent sees. And it is trying to find the coin and jump on the platform. So the training is essentially exactly the same as with the ray perception. It's just using cameras now. So we're going to let this train for a few minutes. Like I said earlier, we have multiple cameras going at the same time, so that can sometimes slow things down. But by choosing that 32 pixels by 32 pixels, hopefully that helps to not slow it down too much, and hopefully it'll train a little faster. For future projects, it may be necessary to increase this sensor width and height to be 84 again or higher. That's just going to be up to you to experiment and see what works well for your project. It almost looks to me like it's already trying to figure out how to get that coin. So let's take a quick look at Tensorboard. This was a previous run I'd done with 84 by 84. Let's see if this... Oh, it doesn't seem to have... It's not ready yet. So I'm going to let this train for a bit, and we'll be back in a couple minutes. All right, I have let this train for a while now. And we can take a look at this in Tensorboard. This is the training, actually the gray run was run with 84 by 84 pixels, and it took about 12 minutes to train. This is my first time trying 32 by 32, which I'm realizing was kind of risky for this recording because I might have had to redo it. But it did eventually train and get to be successful. It just took about maybe 20 minutes to train, 19 or so. So what's interesting about this in my mind is it took longer to train, but the result is very similar. So what that means is, looking at this, we get the same behavior, but we're going to have a much smaller neural network, and it's going to be able to do computations a lot faster. So if we take a look at this, when you stop training, it outputs an Onyx file. So that's in the SimpleViz04 folder. So let me find that. SimpleViz04. I'm going to rename this to Simple Visual Collector, and I'm going to put a 32 in here just for my own awareness of which one this is. I have another one in here from a previous training called Simple Visual 84 Collector. So I'm going to drag this Simple Visual 32 Collector in here. And then we can go into our character in the prefab, and we can update this neural network model. Remember, this one is from the raycast, the ray perception training. And then this one is the 84. Sorry, I want the 32. Okay, so 32. And just to make sure this works, I'm no longer running training. You can see that this has stopped. And I can hit play, and then it should use that neural network to successfully pick up coins. So this is the view from, this is the 32 by 32 pixel view that the agent has. We can switch back to free aspect and just see what it looks like. Otherwise, it seems to be working really well. I'm gonna go to the scene view and we can just take a look at it from here. Seems to be working great, which is really cool. So let's just take a look at the difference between these different neural networks. So this is the one with ray perception. The input is 52 because each ray has multiple input values that get fed in. So it's some multiplied version of, like 5 different inputs per ray. And then if we look down at the bottom, we can see the total weight size in bytes. So we have 81 kilobytes for the total size of this saved neural network. The 32 by 32 pixel one You can see here in the visual observation 32 by 32 by 3, which is an RGB image that's 32 by 32. The total weight size is about 178 kilobytes. And then if we jump up to the 84 by 84, now we're looking at over 800 kilobytes, almost a full megabyte. So you can see how ideally, if you want to keep this small and lightweight and performing as quickly as possible, you really want to optimize for something that's small and quicker to compute, because this just is going to have so many more parameters in it that need to be computed versus something that's simpler. And if you get the same result, and I can show you that really quick, what difference does it make in this case? So I would say don't over optimize on something like this where it's so simple, because we're going to try and make this more interesting in the future, but it is good to know. And the extra training time may be important. It depends on if you're trying to optimize for a faster training neural network or one that is just as successful, but maybe takes a little longer to train. The reality is you only need to train it once, but you may need to run this neural network for years if you use it in a game or in some other application where you're going to be deploying this. That's just something good to keep in mind. So that was using the 32 by 32, and I'll just show you really quick how to switch. So if I go into my camera sensor and I change this back to 84 by 84, and then I switch this to use my simple visual 84 collector neural network model that I had trained previously, you'll see that the behavior is basically the same, but it's going to be a lot more expensive to do those computations. So, you get to decide what you want to do from this point on, and figure out what works best for you. Hopefully you found this video helpful. I think this is really cool that you can use either visual observations or ray perception. If you have any comments, feedback, or questions or requests for future content, definitely let us know in the comments. And as always, thank you so much for watching.